In this web clip, we'll discuss the interference of light, and in particular the interference between two beams of light, or two optical sources. These two sources can be produced in two different ways. You can either split the wavefront, or you can split the amplitude of one original source. Let me explain. Splitting the wavefront, you get, for instance, in this picture, where by using two small apertures, you split the incident wavefront in two optical sources, and these two optical sources, they interfere when they combine on a screen. Splitting the amplitude occurs, for instance, when you consider reflection from a thin film, and where you have the reflection from the top, the first surface, and from the bottom surface. And these two split beams are beams where you split the amplitude of the incident wave effectively, and where you also get interference. And in both cases, the interference is just the addition of two sources, which can be either constructive or destructive, depending on whether the sources are in phase or out of phase. And you see that clearly, for instance, in this picture, where the two sources are two blobs blopping up and down in the water. And you see in some regions there's constructive interference, there's lots, the amplitude's high, and in other points there is destructive interference, where the two sources are out of phase and the intensity is 0. The mathematics of two-beam interference is relatively simple, although you might not say so from this equation. Let me explain. Two-beam interference always depends only on the phase difference between the two sources. So what you do to calculate the amount of two-beam interference is you determine the path length difference between the sources. From that path length difference, you determine, you compare that with the wavelengths of light to see how much the waves are shifted with respect to each other. And as a second point, you might have to consider additional phase differences, delta phi, that you, for instance, get if you get a reflection from a top and bottom interface, which are out of phase. In total, the phase difference between the sources that we consider is thus given by the path length difference, delta L divided by lambda, multiplied by 2 pi, because every oscillation you have 2 pi of phase, and possibly with the addition of a phase jump at an interface. So this is the mathematics spelled out more completely. If you calculate the total field, you have to sum the field of one source and the field of another source, and these phases, or the phase difference between the sources, that's the crucial part. And to get this equation right, you might remember, you hopefully remember, the phasor diagram that I showed previously in one of the previous lectures, where phasors are arrows in the complex plane that rotate at the rotation rate omega, angular frequency omega. And if you have two oscillations with a phase difference, you have two arrows in the complex plane that you have to add to a total phasor with an average phase and with an amplitude that contains the phase difference. And then finally you have to consider that the intensity of the light is, of course, something like the amplitude squared, which means you get the square of this cosine, half the cosine difference, which means you get this expression. And there are variations on this principle. For instance, variations where you consider sources of different amplitudes, phasors with different length, or where you consider sources with different optical polarization. But these I'll discuss during the lectures. The interference of light was first demonstrated by Thomas Young in 1802 in the following way. He used a slit, he used a screen, I should say, with two slits illuminated by a single source, in his case light from the sun, and he observed the light passing through the slits at a distant screen. And if you do this properly, you can see oscillations in the intensity at the screen, interference fringes. And by that observation alone, he demonstrated that light is a wave and not a particle. So a question you might ask is, which parameters determine the spatial period on the screen? Something I'll explain in detail in the next sheet, but let me first give the general argument. So what would you expect? I sketched a couple of parameters that are important here. The length, the distance between the sources and the screen should obviously be in there, and you expect the period of the oscillations to be proportional to this distance. If the screen is further away, the period is likely to be larger. Then, a second parameter in there is probably the distance between the slits. But there is a third parameter that you might not immediately think of, and that is the wavelength of light. The wavelength of light also goes in there. So you have to find something which is proportional to a length, and then probably also contains a wavelength and a distance between the slits. And what I'll demonstrate in the next slide is that the actual equation looks like this. The period of the oscillations scales with the length, the wavelength, and the distance of light, at least if the angles involved are much smaller than 1. So if you're paraxial. This slide shows the idea of a more complete calculation of the interference pattern. So what we consider is light with a single wavelength, fixed geometry of course, and we consider the interference at sufficiently far away from the slit. So this distance L has to be large, and to be more precise, it has to be larger than d squared over lambda, to be in what's called the Fraunhofer regime, or the far field regime of diffraction. And if you're very far away from the slit, then the two light sources being emitted by these two slits to this distant screen, they produce more or less parallel beams that interfere far away. So when you talk about the phase difference, or want to calculate the phase difference between the light from this source 1 and source 2, slit 1 and slit 2, all you have to think about is the path length difference between these two passes, which here, if you magnify it a little, you see here the path length difference, and that path length difference depends, among others, on the observation angle with respect to the surface normal. So where do you observe the interference? And if you think a little bit harder, then you recognize a small triangle in here, and you'll easily understand that this path length difference is equal to the distance between the slits multiplied by the sine of the emission angle. And if you then include this factor 2 pi radians per oscillations, and compare the path length difference with the wavelengths of light, you realize that the criterion for constructive interference, which is the criterion that the phase difference is a multiple of 2 pi, translates into the criterion that the sine of this angle, this sine, should be equal to the ratio lambda over d, this lambda over d, multiplied by an integer, where the integer denotes how large the phase difference precisely is in multiples of 2 pi. You've seen this picture before. This is the picture of the famous Young's double slit experiment, the experiment that Young performed in 1803 or 1802. And you might wonder why it took so long to perform this experiment. Why only in 1802? What makes this experiment so difficult? Well, the first reason, an obvious reason, is that the wavelength of light is incredibly small. If you think about visible light, the wavelength of visible light from blue to red is less than a micron, 0.4 to 0.8 microns. So that means that slits typically have to be small, thin, to make this experiment work. But there are two other reasons that I'll explain in the next slides, and are maybe less obvious. two other reasons that are summarized in this phrase. You need a monochromatic point source. So what does it mean? On the one hand, you need a small spectral bandwidth, or you need light of a more or less fixed color. If you have light from the sun containing all colors, then things get messy at the screen because you have a multiple of colors, all colors, different interference patterns, and it's difficult to observe interference. So you need spectral coherence. On the other hand, you need a small source. Here ideally described as a point source. And that refers to the word you need spatial coherence of the light, a concept I'll explain in 2 slides to come. I already mentioned that one of the requirements to observe Young's interference is that you need a sufficiently large spectral coherence, or you need a source that is sufficiently single color. And the argument here is demonstrated in 2 pictures. The top picture is an idealized description of what you would see or expect to see if you have 2 colors of light in the incident beam. 2 colors which are somewhat similar but still different, such that each of the colors produces an interference pattern, and the interference patterns have a slightly different spacing, right? I mean, the longer the wavelengths, the larger the spacing in the interference pattern. So if you have that, 2 interference patterns with a slightly different period, if you add these 2 interference patterns incoherently, you just add the intensity, you see that the sum of the 2 is an interference pattern that gradually disappears. And that argument applies. The stronger, the more wavelengths are involved. And that's shown here in the bottom picture, where you see interference from multiple colors, basically light from a lamp that contains a couple of spectral bands. And you see here that the blue light has a small interference period, whereas the red light has a much larger interference pattern. So you see in the first fringe, you see a rainbow, and then in the second, third fringe, at some point, rainbows even overlap. So if you would look at the intensity in this pattern, you might see some oscillations here, but then gradually, or actually quite quickly, the oscillation in the intensity disappears, and in the intensity you only see like 3 fringes. Very difficult to observe. The second argument that I gave why the observation of Young interference is difficult is that you need sufficient spatial coherence, or a small source. And with spatial coherence, I mean that the light emitted by source 1 and source 2 should be sufficiently similar. And the problem is as follows, and maybe I should read out this sentence aloud. I mean, if you have a slit that is illuminated with light from a large source, you not only have light from one part of the source, but you also might have light from a different part of the source, say this part of the source. And if you trace that light and wonder where the point of constructive interference is, you will realize that if the source is shifted, then also the point of constructive interference is shifted. So the problem you're facing if you have a large source is that each part of the source emits its own light, produces its own interference pattern, and these interference patterns might be shifted with respect to each other. And then if you add them and look at the overall intensity as a function of transverse position, you'll notice that the bigger your source gets, the more blurry the interference pattern gets, up to a point where you don't see the interference at all at this point. So you need sufficient spatial coherence, you need a sufficiently small source to really observe the interference. The second type of interference that they like to introduce is the interference that you get when you split the amplitude of the incident light. Right? You have incident light, it gets reflected from a first interface between medium 1 and medium 2, and then part of the light propagates and gets reflected from a second interface between medium 2 and medium 3. And these two reflections, they combine and they can interfere constructive or destructive. So you see an interference pattern. If you look at the reflection from a thin film, and here are some examples of thin films, for instance, soap bubbles, reflection top and bottom from the soap bubble, or here reflection from an oil film, where you either have reflection from the top or the bottom of the oil film, or a third case, reflection from two glass pieces that I'll discuss in a minute. Anyhow, in these circumstances, what's important to calculate whether the interference is constructive or destructive is again the phase difference between the two optical paths that contribute. And this phase difference has two contributions. On the one hand, you just have to look at the path length difference here of the first reflection in this case and the second reflection. And that path length difference, of course, contains 2D, but also the cosine of some internal angle, to be discussed later, and the wavelengths of light. You divide by the wavelengths of light to make the comparison and to transfer path length differences into phase differences. And on the other hand, for these type of reflections, you have to think about whether reflection from an interface, whether the refracted light is in phase or out of phase. Again, details will follow. This slide shows some of the details that I already promised. We consider incident light, first reflection, second reflection, and wonder how do these two beams, 1 and 2, interfere with each other. And obviously that interference depends on the path length difference between these two paths. And naively, you might think that if you work at an angle, at non-normal incidence, that this path gets longer than this up and down path of 2D. But that's not the case. If you do the exact calculation to calculate the optical path length difference between this path and this path, you realize that in this calculation, of course, you have the paths from A to B and B to C multiplied by the refractive index of that medium to get the optical path length. But you have to subtract the optical path length of this AD path. So the length of AD times the refractive index in the top medium. And if you do the calculation, you find, to your surprise, that if you work at an angle, the optical path length difference between the second reflection and the first reflection decreases if you work at an angle. It doesn't increase, it decreases. And the resonance that you observe, the color, acquires a blue shift. But I'll do the derivation in more detail in the lecture. This slide shows an example of interference, and in particular of the interference that you observe upon reflection from a freestanding film, like this film of soap. That interference, freestanding film at normal incidence, is as usual determined by the phase difference between the first reflection, the reflection from the first interface, and the reflection from the second interface. And this phase difference, of course, primarily depends on the path length difference in the film. So if you have a film thickness D, then the path length difference between these two paths is 2D. And to convert path length difference into wavelength, into a phase difference, you have to divide by lambda. And quite silly, I recognize. You, of course, also have to multiply by 2 pi, because in every oscillation, there are 2 pi radians. So there should be a 2 pi here and a 2 pi there. And you might recognize my notation. Here I divide the path length difference 2D by the wavelengths in the medium. You can also do it in a different way, where you say, well, I consider the optical path length, so the refractive index times the thickness of the film, and I divide by the wavelength in vacuum. Result is of course the same. What is important though in this equation is that there's also this funny factor, funny term, 2 pi, pi. And this pi originates from the observation that the reflection at the first interface, so from medium 1 to medium 2, and the reflection at the second interface from 2 to 3, they differ by a minus sign or by a phase pi. And the reason, of course, is that if you go from an optically thin to an optically thick medium, the reflection has a minus refraction amplitude, whereas if you go from optically thick to optically thin, there is no minus. So let me discuss a few subtleties here, or intriguing questions you might say. And the first one is, what is the reflection of this freestanding film if the thickness goes to 0? Well, you sort of already see it here in this soap film. If the thickness goes to 0, the total reflection goes to 0. So there is apparently destructive interference between the reflection from the front and the back facet. And you get that destructive interference precisely because of this pi, because of the observation that the reflection from the front and the reflection from the back are naturally out of phase, even if there is no path length difference. A second question you might ask is, between which values does the intensity reflectivity vary for water soap? And that, of course, depends on the refractive index of the water soap, which is 1.33. And what you have to use is you have to use the equation R is reflection amplitude is 1 minus the n divided by 1 plus n. And if you plug in this number, and I have to do it by memory, is approximately 1 over 4. So that means that the reflectivity of this film, the reflectivity of this film is approximately 1 over 49, so 2% intensity reflectivity, right? And you might have seen that I square, of course, to get from amplitude to intensity. This is of a single interface, and now that you have 2 interfaces, 2 reflections, you have to add them. You have to add amplitudes. The amplitude gets twice as big, so the intensity gets 4 times as big. So for constructive interference, the reflectivity, the intensity reflectivity of the total film is 4 times 2%, 8%. You might also wonder between which values the intensity transmission varies, and that argument is relatively simple. The transmission, the intensity in transmission is 1 minus the intensity reflection. There's no absorption of light, and that means that if the reflection varies between 0% and 8%, destructive constructive interference, the transmission varies between 92% and 100%. This is mainly a cute picture to show how the interference in the thin film of soap that I showed previously can be used to determine the thickness of the film. So if you consider a soap film at normal incidence, illumination at normal incidence by sunlight, then you notice these beautiful color variations where the color depends on the thickness of the films. And you might realize that this picture is rotated by 90 degrees. It's a hanging soap film, which is very thin here and gets thicker down the way. and you see these beautiful changes in colors. And the statement is that you can use these colors to reasonably precisely determine the thickness of the film, at least up to a point where the thickness is less than a micron, because if the film gets thicker than a micron, then the colors sort of fade out, they get blurry. If you want to know precisely how this works, you need to do some thinking, because the colors that you see, they're basically there because other colors are filtered out. So for instance, if you look at this thickness of 220 nanometers or so, the film looks blue at this thickness, and it looks blue because the red part of the spectrum is filtered out. It disappeared because of destructive interference. So for this thickness, for this point, for this thickness, the thickness of the film is approximately equal to the wavelength of the red that you filtered out divided by 2, where again for the red I refer to the wavelengths of red in the medium. So if you want to relate that to the wavelengths of red in the vacuum, you get this refractive index at the bottom. And you recognize if you put here 600 nanometers, here a refractive index of 1.33, you approximately get this thickness of 220 nanometers. So it fits. A different type of interference, but again based on splitting of the amplitude of the incident light, is the interference that you get when you, for instance, look at a lens, a curved piece of glass, positioned on a flat piece of glass. And if you look at that, what you effectively see, you see a pattern that originates from interference. Again, interference between light reflected from this interface, glass air, and light reflected from that interface. And the third reflection from the top interface is typically far away, out of focus in the observation, and therefore not really visible. So if you look at these two pieces of glass, what you typically see is you see an interference pattern comprising rings, where the spacing between the rings decreases with increasing radius. And these rings are called Newton rings. And if you have a nice ring pattern like here, you know for sure that you have a good lens, that the curvature here is like a spherical curvature. Whereas if you have a bad lens, you might have a weird interference pattern. And so, again, as usual, the phase that we observe, or the interference that we observe, is related to the phase, which now depends on the position on the radius, and this phase is a path length difference divided by lambda, and then multiplied by 2 pi to go from path lengths to phases. So, a tiny remark. You might wonder, why is the center of this interference pattern dark? You can think of 2 reasons. The first is, if you look at the center, the 2 glass pieces touch. And if the 2 glass pieces touch, you basically don't have reflection, because you go from glass to glass. There's no reflection. So in reflection, you don't see any light. It's dark. The second reason is more subtle and refers to the point where the glass almost touches, but not precisely. And that's, again, the argument that I used previously, namely that the reflection from medium 1 to medium 2 is minus the reflection amplitude from medium 2 to medium 1. So at the point where the glass pieces almost touch, the reflection that you get going from glass to air has a certain sign, but if you go from air to glass, you have the opposite sign. So these reflections are out of phase, interfere destructively, and the total reflection is 0, and hence in the reflected intensity there is a 0, there is a dark point there. As a final example of interference, we'll consider the Michelson interferometer. an interferometer which again is based on the splitting of the amplitude of the light. And the story is as follows. In a Michelson interferometer, you have an incident beam of light incident on a beam splitter. A beam splitter is a device which reflects part of the light and transmits part of the light, typically in a 50-50 ratio, but not necessarily so. And in a Michelson interferometer, each of these beams hits a mirror, gets reflected back, hits the beam splitter again, and part of that light is transmitted or reflected. And so at the output of the Michelson interferometer, you have two contributions. One contribution from the light that originally reflected and then transmitted with an amplitude reflection times transmission. And the other contribution is from the light that is first transmitted and then in the second run reflected. The amplitude of that contribution has this R prime, where R prime is the reflectivity of the beam splitter from the back end. And it's the same as the reflectivity from the front end, apart from a minus sign. Hence, these two contributions have equal amplitude, and hence the interference that we have at the end of the beam split is a full interference, where if the interference is destructive, the light is gone. If you then wonder what the interference pattern will depend on, it's the usual story. It depends on the path length difference between these two passes in the Michelson interferometer, and that path length difference, of course, contains the factor 2 because of the up and down path and the difference in the length of the two arms. You have to compare that with the wavelengths of light, and then the pattern that you will see depends on the alignment of the mirrors and the beam splitter, but also on the shape of the incident beam. If you use a diverging beam, a divergent beam, at the input, you see intriguing rings. If you use a parallel beam, you see stripes. But I'll demonstrate that in more detail in a separate web clip. Then finally, and as a teaser, something I'll explain during the lectures, you might wonder what happens to the light if the interference at this output port is not constructive but destructive. So if these two contributions are out of phase, interference is destructive and there is no light visible. So the question then is, what happened to that light? Think about it and we'll discuss it during the lecture. This slide summarizes the interference that you can observe if you interfere two sources of light. I started by pointing out that this interference can happen in two different ways. You can split the wavefront, the incident wavefront, as you do in Young's double slit experiment, or you can split the amplitudes of light. In Young's double slit experiment, you nicely see constructive, destructive interference on a screen. You see a full pattern. In the other case, where you split amplitudes, I gave a couple of examples. For instance, here the thin film, interference in a thin film. But I also mentioned the Michelson interferometer as another case of interference with a beam splitter. In both cases, in all these cases, the recipe to calculate how much interference you have is relatively simple. All you have to do is you have to calculate the phase difference, delta phi, between the two sources. And that phase difference depends on the path length difference compared to lambda. And then typically with a 2 pi, or always with a 2 pi in there to go from oscillations to phases. And for reflection from films, you always have to think about the sign of the reflection, whether the reflection from the top and the bottom surface are naturally in or out of phase. Thank you for your attention.